In this lecture, we shall introduce statistical inference and we shall discuss the concepts of point estimation, interval estimation, and testing of hypothesis. Now, what is statistical inference? Suppose we want to know about some unknown nature of a population. Most often, it is not possible to enumerate the whole population. In that case, we have to resort to a part of the population which we call a sample. So from investigating the sample, we have to guess or find some likely value of the population characteristics. In a nutshell, this is what we mean by statistical inference. As we will move deep into the lecture, we will understand the concepts more elaborately. But before going into these concepts, we have to understand some prerequisites which are very important. Otherwise, we won't be able to do mathematical treatments to the statistical theory of inference. First, we will consider the measures on a discrete probability distribution. So we start with expectation or mathematical expectation. Let x be a discrete random variable that takes up the values x1, x2 up to xn or x1, x2 ... with the corresponding probabilities p1, p2, pn or p1, p2 ... If you can recall, when we talked about probability earlier, we said that a discrete random variable can assume either a finite number of values or countably infinite number of values. So here x1, x2, xn will represent a finite number of values. On the other hand, when we write x1, x2 ... that will represent countably infinite number of values. Here we write pi is equal to probability x is equal to xi for all I, such that the total probability, that is summation over I pi, is equal to 1. As you can see on your screen, expectation of x is equal to summation xi pi. Observe that summation xi pi can be written as summation xi pi divided by summation pi, because we know summation pi is equal to 1. Thus, expectation is nothing but the arithmetic mean in the probability setup. Why? Because when we talk about a frequency distribution, say x is a variable that takes up x1, x2, xn, the values, together with the corresponding frequencies f1, f2, fn, then we say that the arithmetic mean is x bar is nothing but summation xi fi divided by summation fi. So here, just we are translating this idea into the probability setup. Instead of fi, the frequencies, we have the probabilities. So that means xi's are weighted by the probabilities. So we can say that expectation is nothing but the arithmetic mean in the probability set. We have expectation of x is summation xi pi. Now pi is nothing but probability x is equal to xi. So we can write summation over x into probability capital X is equal to small x. Now from earlier knowledge we know that probability capital X is equal to small x can be written as fx, where fx is the PMF. So expectation of x can alternatively be written as summation over x into fx. We take an example. Suppose we toss an unbiased coin 3 times. We denote by x the number of heads obtained in these 3 tosses. So we have to find out the expectation of the number of heads, that is expectation of x. We have already come across this earlier when we talked about probability distribution in general, that here x will take up the values 0, 1, 2 and 3 with the probabilities 1 by 8, 3 by 8, 3 by 8 and 1 by 8, the total probability being 1. Now by the formula of expectation, if we calculate the expectation, you can see it will come out as 0 into 1 by 8 plus 1 into 3 by 8 plus 2 into 3 by 8 plus again 3 into 1 by 8, which comes out to be 1.5. That means when we toss an unbiased coin 3 times, the expected number of heads obtained will be 1.5. Now this is a bit surprising. Why? See, when we toss a coin 3 times, we'll never get 1.5 heads. Either we'll get 0 head or 1 head or 2 heads or 3 heads, but never 1.5. So is this result absurd? No. Here we have to understand the concept of expectation, which will be very much useful in statistical inference. This basically means if we repeat this experiment of tossing the coin 3 times a very large number of times, then in some of the times we'll get 0 head, in some of the times we'll get 1 head, in some 2 and in some 3. If we calculate the arithmetic mean, of this frequency distribution, that will come out as 1.5. This is why expectation is also called the long run arithmetic mean. That means when the total number of observations is very large. Variance. We define it as expectation of x minus ex whole square, which can alternatively be written as ex square minus ex whole square. It is analogous to the formula of variance in the frequency setup. If you can recall, in the frequency setup, the formula of variance is 1 by n summation xi minus x bar whole square, which can alternatively be written as 1 by n summation xi square minus x bar square. We start with a problem. Suppose a bag contains 5 white and 3 black balls. 3 balls are drawn randomly from the bag. We have to find out the expected number of white balls drawn. So the bag contains 5 white and 3 black balls. Now see, we are drawing 3 balls. So either it is possible that we may not get any white ball out of the 3 balls drawn, or it is possible that we may get 1 white ball. It is possible that we may get 2 white balls, or it is possible that all the 3 balls drawn are white. That means if I denote by x the number of white balls drawn, x will take up the values 0, 1, 2 and 3. Now what is probability x is equal to 0? X is equal to 0 means no white ball. That means all the balls drawn are black. So it will be 5c0 into 3c3 by 8c3, which will come out as 1 by 56. Similarly, probability x is equal to 1 means 1 white ball. So from 5 white balls we'll draw 1, 5c1, and from 3 black balls we'll get 2 black balls. Obviously in all 3 balls we are drawing, so 3c2 by 8c3. In all 3 balls are being drawn out of 8 balls. That comes out as 15 by 56. Similarly, probability x is equal to 2 and probability x is equal to 3 will come out as 30 by 56 and 10 by 56. You can easily check that the total probability will come out as 1. And using the same formula of expectation, the expectation of x comes out as 1.875. That means I'd like to again reiterate the thing that when we are drawing 3 balls out of 8 balls, we can never get 1.875 white balls. Either we'll get 0 white ball, 1 white ball, 2 white balls or 3 white balls. But believe me, the computation is correct and we are getting the expected number of white balls drawn as 1.875. So again, this will mean that if we repeat this experiment of drawing 3 balls out of 8 balls of the given composition a very large number of times, then the arithmetic mean of the frequency distribution of the number of white balls will come out as 1.875. This again justifies the expectation as the long run arithmetic mean. What I'd like to mention here is this: you should always remember that whenever we are talking of expectation, we are talking of number of observations and in the sample, and many a times we will talk of large sample. That means a large number of sample observations. We come to another problem now. Suppose a player A gains rupees 16 from another player B for getting at least 1 hit and loses rupees 40 to B otherwise when an unbiased coin is tossed 3 times. We have to find the expectation of the gain of A. So you see, what do we mean by loss or loses rupees 40? What will be the gain of A in that situation? It will be minus 40, right? Just keep this in mind as we move into the solution. So we denote x by x the gain of player A, and we can see that x can take up the values either 16 or minus 40. Probability x is equal to 16 means probability at least 1 hit, because we have seen that as per the problem that player A will gain rupees 16 if he gets at least 1 hit. At least 1 hit means what? We have solved this type of problem earlier also. 1 minus probability no hit. That means 1 minus probability of TTT. The coin is unbiased, so that will be 1 minus 1 by 8. So it will come out as 7 by 8. Also, probability x is equal to minus 40. We said that he will lose rupees 40 otherwise. Now what do you mean by otherwise in this situation? Otherwise of at least 1 hit. That means no hit. So that means probability of TTT, that will come out as 1 by 8. So again we apply the formula of expectation. We'll get 16 into 7 by 8 plus minus 40 into 1 by 8. It comes out as 9. So again I will want to reiterate the thing that A will either get rupees 16 or A will lose rupees 40. So what is this rupees 9? That means if the game is played a very large number of times, then on an average, A will get rupees 9. Now mind you, when the random variable takes values with some units, then you have to put the unit in the expectation as well. So that is why you can see on your slide that in the last line after 9, within bracket, rupees is written. So this is very important. We go to another problem. Suppose a person gets rupees 2x plus 5 when x denotes the number appearing when a balanced die is thrown once. We have to find the expected gain of that person. Now here, can you tell us what is the value that x can take up? Or equivalently, what are the values that can be taken up by twice x plus 5? So here we are not going to find out expectation of x, mind you. Here we are going to find out the gain of the person, which is twice x plus 5. Let us see how we can solve this sum. Clearly, when a die is rolled, x can take up the values 1, 2, 3, 4, 5, 6. So the die being balanced, each outcome will have the probability 1 by 6. Then by the problem, the gain of the person being twice x plus 5, it will take up the values 7, 9, 7 when x is equal to 1, 9 when x equals to 2 and so on up to 17. So expectation will be 7 into 1 by 6 plus 9 into 1 by 6 plus 11 into 1 by 6 plus 13 into 1 by 6 plus 15 into 1 by 6 plus 17 into 1 by 6. So we have taken 1 by 6 common and it comes out to be 12. Next we'll go into the moments and measures of skewness and kurtosis. We have several moments. So we have to define these moments one by one. The rth order moment of a random variable x about an arbitrary constant a is defined as expectation of x minus a whole to the power r, and we denote it by mu r, then within bracket a to denote the arbitrary constant a. We can observe that mu naught a equals to 1. What do you mean by mu naught a? In place of r we have 0. So it will be in the formula expectation of x minus a whole to the power 0. Anything to the power 0 is 1. So expectation of 1 is 1. Expectation of constant, it does not vary. So the mean will be 1. Next we go to the rth order row moment, which is defined as mu r dash, that is expectation of x to the power r. Here also we can see that mu naught dash is equal to 1, while mu 1 dash, that is expectation of x to the power 1, which is simply our expectation ex. The rth order central moment of a random variable x we defined as mu r, that is expectation of x minus ex whole to the power r. Clearly when r equals to 0, again this will be equal to 1, so mu naught will be 1. What about mu 1? That is ex minus ex, that is expectation of x minus expectation of x, which will be equal to 0. And mu 2, I hope this looks familiar to you, it is nothing but the variance of x, expectation of x minus ex whole square. Now why do we need these moments? Because we want to know the skewness and kurtosis of a probability distribution. Now see the diagrams that are on your screen. First concentrate on the diagram at the central position. You see the two tails of the diagram are equal. This is called a symmetric distribution. On the other hand, you see the diagram on the right hand side, the longer tail is towards the positive direction of the x-axis. So this distribution is called a positively skewed distribution. On the other hand, if we go to the left hand side distribution, you can see the longer tail is towards the negative direction of the x-axis. It will be called a negatively skewed distribution. It can very easily be seen that for a symmetric distribution, mean, median and mode are same. For a positively skewed distribution, mean is greater than median and that is greater than mode. On the other hand, for a negatively skewed distribution, mean is less than median and that is less than mode. Now we go to the measure of kurtosis. It is gamma 1, which is mu 3 by mu 2 to the power 3 by 2. Mu 3 and mu 2 are nothing but the third order and second order central moments of x respectively. And how do we know what is the skewness of a distribution? Through this measure, it can easily be seen that gamma 1 is positive for a positively skewed distribution, negative for a negatively skewed distribution, and 0 for a symmetric distribution. Now we go to kurtosis. It is another characteristic of a probability distribution. By kurtosis, we mean the degree of pickedness of a distribution. You can see in the diagram, there are three distributions with different pickedness, that is different types of peaks. There is a moderately picked distribution, there is a distribution which is more picked than a moderately picked distribution, and there is a distribution which is less picked than a moderately picked distribution. So the distribution which is moderately picked is called a mesokartic distribution, also termed as normal distribution. A distribution which has more pickedness than a mesokartic distribution is called a leptokartic distribution. Finally, a distribution which is less picked than a mesokartic distribution will be called a platykartic distribution. It is to be noted that there may be distributions having same mean and same variance, but they differ in their shapes. Differ in their shapes in terms of their skewness and their kurtosis. So skewness and kurtosis are called the shape parameters of a distribution. Now we go to the measure of kurtosis. It is gamma 2, which is mu4 by mu2 square minus 3. Again, mu4 is nothing but the fourth order central moment as we defined earlier in general, and mu2 is the second order central moment or the variance. It can be shown that for a leptokartic distribution, gamma 2 is greater than 0. For a mesokartic distribution, gamma 2 is equal to 0. And for a platykartic distribution, gamma 2 is negative. Sometimes we consider two other quantities, beta 1 and beta 2, in connection with skewness and kurtosis of a frequency distribution. Beta 1 is defined as gamma 1 square, which is clearly mu3 square by mu2 cubed. On the other hand, beta 2 is defined as gamma 2 plus 3, which is mu4 by mu2 square. Now tell me, can we use beta 1 as a measure of skewness? So we have to understand whether beta 1 can be regarded as a measure of skewness. No, beta 1 cannot be used as a measure of skewness. You see, beta 1 is gamma 1 square. Gamma 1 takes up positive values for a positively skewed distribution and negative for a negatively skewed distributions. So gamma 1 square can never be negative. So that means from beta 1 we can only understand whether a distribution is skewed or not. If a distribution is skewed, we won't be able to say whether it is positively skewed or negatively skewed. So that is why we have to stick to gamma 1 as a measure of skewness. On the other hand, beta 2 can be used as a measure of kurtosis. That is simply because when we are talking of gamma 2, we compare the value of gamma 2 with 0. Positive for a leptokartic distribution, negative for a platykartic distribution, and so on. Similarly, the value of beta 2 can be compared with 3. So if it is greater than 3, we say that the distribution is leptokartic. If it is equal to 3, we say that the distribution is mesokartic. On the other hand, it is less than 3, then we say that the distribution is platykartic. Now, we'll come to actual statistical inference. We have understood the prerequisites, so now we will dive into statistical inference. Any statistical inquiry has as its goal the acquisition of knowledge about some unknown characteristics of a population. And these unknown characteristics may be what? Population mean, population variance, population proportion, etc. So these will be called parameters. The inquirer will generally have information regarding a part of this population, which is called a sample. That means the population is unknown to the investigator. So the parameters are unknown to the investigators, but we will have a sample in our hand. The central problem of statistics, this is a central problem, mind you, the most important problem of statistics is then to devise methods of inferring the nature of this unknown parameter from the known nature of the sample. This central problem is called the problem of statistical inference. So the population is unknown to us, and in most of the situations we won't be able to enumerate the whole population, maybe due to lack of resource, or maybe that the population cannot be enumerated at all. In these situations, we will resort to a sample. We will draw a sample from the population randomly, and we'll have the sample observations in our hand, and with the help of these sample observations, we will try to guess the unknown parameters. Now, one point I mentioned just now, that it may be that the population cannot be enumerated. We can think of such an example. Suppose a manufacturer produces electric bulbs and he is interested in the life of the bulbs produced by him. So how to measure the life of a bulb? The bulb is put on a higher voltage than what we use in our domestic homes, and the time is measured with that voltage, with that higher voltage, how long it takes to get fused. Then with some mathematical calculations, they find out that how long the bulb will survive in the normal domestic voltage. Now, if I want to enumerate the whole population, what does it mean? I have to fuse all the bulbs which are being produced by me. So what I'll sell? So in these situations, you can understand that enumeration of the whole population is impossible. It is not due to lack of resource. It is because of the practicability of the whole thing. So in such situations, we have to resort to sample. And believe me, in almost all situations, we resort to sample. And that is why population censuses are carried out once in 10 years in most of the countries. So that's why these censuses are known as decennial censuses. Let's come back to our point. There are several types of statistical inference. Basically, there are two main types that we will discuss here. The first type is this: the characteristic of the population that we are interested in may be completely unknown, and we may have to depend entirely on the sample observations to form an idea about. Now we will use a terminology that to estimate these characteristics. This type of inference is called estimation. That means we do not have any idea regarding the population. We have to depend solely on the sample. Estimation may again be of two types: point estimation or interval estimation. In the first case, that is, in case of point estimation, we compute a single value on the basis of the sample observations and put forward this value as a likely value of the corresponding population parameter. The statistic which is used for this purpose is called an estimator, and its value for a given set of sample observations is called an estimate. Let us try to understand this point. Suppose I want to find out the per capita average income of Indian population. So if I want to enumerate the whole population, then what I have to do? I have to go to each and every Indian. I have to get the data on their income and then find the average income. This is impossible, practically impossible. So I'll take a random sample from the whole population so that the persons from higher income group as well as from lower income group may belong to the sample. Now, suppose I calculate the average income of the members belonging to the sample. Say let it be X bar. So this X bar will be called an estimator. And suppose for my sample, the value of X bar comes out to be, say, 20,000 rupees. Then 20,000 will be called an estimate. So we want to find out the population mean, which is impossible. So we resort to a sample, we take a sample, calculate the sample mean. The sample mean itself, which is a statistic, will be called an estimator, and its value will be called an estimate. Mind you, this guess, basically we are guessing the population mean by the sample mean. So this guess may be correct, may be wrong. We have to take that risk. On the other hand, in case of interval estimation, we compute two values on the basis of sample observations and put forward the interval between these values as likely to contain the true value of the population parameter. That means I want to find out the average income of the whole Indian population. I compute two values, say 15,000 and 25,000, and I say that the average income of the whole population will lie between 15,000 and 25,000. That means instead of picking up a point, we are now picking up an interval to estimate the population parameter. This is called interval estimation. So these two constitute estimation, the first type of statistical inference. In the second type of statistical inference, which is called the testing of hypothesis, we start with some tentative idea regarding the unknown population, and on the basis of the sample observations, we try to judge how tenable or how justifiable this idea is. Suppose I am the producer of, say, electric bulbs. I say that 1% of my products are defective. This is a tentative idea because just a while ago I said that enumeration of population is not possible in case of electric bulbs. So my tentative idea, by looking at my process, looking at my sales, I tentatively say that 1% of my products are defective. Now, as a customer, how one will know whether my claim is justified or not? The customers may buy some bulbs produced by me, and they can find out what proportion or what percentage of the bulb in the sample are defective. So from that, we can form an idea whether my claim is tenable or justifiable. This tentative idea is called a hypothesis, and the process of judging its validity or justifiability is known as the testing of hypothesis. In the later sections, we will deal first more about point estimation, and then we will move over to testing of hypothesis. In point estimation, obviously we have to study what estimators we will choose, what are the criteria of good estimators, so on and so forth. And in testing of hypothesis, we will study the actual process of judging the validity of a tentative idea. Thank you.